asked me to speak on just some general aspects of the mineral system concept. Now, this is the mineral system concept is, you've heard the word. It means different things to different people. So I just want to give you a bit of an overview of where the mineral system concept is at. And I'm a big believer in giving you the conclusions so that when you wake up at the end, you remember exactly what you were supposed to hear. And that number one is that mineral systems are dynamic, complex systems. Now, that's no surprise to anyone, but a thing that we've come to realize is that they're exhibiting a sort of behavior called self-organized critical behavior. And understanding this, the physics of the process, actually changes how we look at the questions about mineral systems. And it means that inherently they should be predictable rather than random alignment of variables. The critical elements of a mineral system have evolved from the classic trilogy of source, pathway, and trap from the petroleum world, and into the minerals world that's a much more complex system. Now we propose that there's fertility, favorable whole lithosphere architecture, favorable transient geodynamic triggers, and those are the things that combine to form high-quality mineral districts, and you have to preserve the depositional zone after mineralization so that you can discover it at an economic depth. And the key challenge that I see that people have, and that includes our group as well, the challenge that people have in applying the mineral system concept is always comes down to one of scale. And that is that you must be matching the scale of the decision you're making in terms of area selection to the relevant process that's operating in the mineral system at that scale. And the example, the best example being one of deposition. As you can see, I have preservation of the depositional zone off to the right, and that's because at the scale of regional exploration decisions, the actual site of deposition isn't relevant. Right? It's the next scale down of problem. Okay, so this just highlights the problem that we're facing using the Yilgarn as an example. Okay? Now, many people have seen me use this example before. It takes 1 billion years to get that piece of real estate together. Okay? But as far as we can date those gold deposits that are there in yellow, they all come up in the same geological weekend, a window of around 50 million years generally, plus or minus. And the key aspect is they're not randomly distributed, they cluster. So why do they cluster? If we could actually get some constraints on what causes the clustering of high-quality mineralization, now we're onto something in terms of the predictive space, and especially as we move into areas that are under challenging cover, blind to previous exploration and particularly detection technologies. So when we think about mineral deposits, we often have in our mind pictures like this. Right? So pictures of deposit models. These are vessels that contain all of our knowledge about the processes that have caused mineralization in and around the site of the deposit. And so it's translated to the concept of footprints, where we look at footprints being essentially the leakage of heat, fluids, elements in and around the zone of mineralization, giving us possible pathfinders or vectors to ore. And this has been useful in terms of finding partially buried systems and in terms of, in drill programs, in terms of direct detection into ore, but it also has led to many false positives. I mean, one of the aspects of deposit models is that they're analog models. They're built at the deposit scale from the inside out, and they're less effective coming from the outside in, right, which is the problem we have, especially when we're looking undercover. They're also challenged to distinguish size or quality of systems because decades of research have shown that small deposits look very similar to large deposits. Histories of fluids, alteration styles, etc., they're just smaller. So that doesn't help us in selection either. And because of this, they actually have limited predictive power at larger scales. And so when you look through some reviews of exploration in different terrains, you don't see a lot of credit given to the conceptual side of the targeting. It's usually towards the detection side of the exploration that the discovery credit is given. And of course, these types of models are limited when you're undercover because we're talking only a few tens of square kilometers that even the largest of these systems have an expression, and we're making decisions at scales a lot larger than that before we get down to decide where to put the drill hole. So, when we're, especially when we go in challenging areas, undercover, new mineral districts, low data density, it's the largest scale footprint of the deposit that's relevant to the targeting model. And they differ substantially from how we traditionally look at these deposit footprints. So this is an example from North America, and it shows the dolomite front in the Phanerozoic carbonate sequences. Why is it important? Well, only because every single Mississippi Valley type deposit sits along that front. Right? So this is a continental scale expression of the mineral system in this district. Similarly, many of you have seen this section numerous times through Olympic Dam, showing a combination of washed out areas in the seismic, a conductive zone in the magnetotellurics, which is the color overlay, and the gravity inversions showing the mass anomalies and the chimney of conductive material sitting below Olympic Dam. So it shows that some of the signatures to these mineral systems are also transcrustal and often translithospheric in scale as well. And we're not going to find those with our traditional exploration data sets. So this takes us to thinking about systems. Much like the petroleum industry has gone to, nobody goes around looking for oil seeping out of the ground anymore, right? Yet in the minerals world, that still tends to be our mindset to some degree, although in a little bit of a more sophisticated fashion, that's essentially what we're doing. So we need to move more like the petroleum systems has and go into systems thinking. So the advantage of the mineral system is that it's process-based rather than analog-based. It has substantial, because of that, it has substantial predictive power compared to those traditional deposit model approaches. And in that it has the ability to predict new mineral districts when there's no previous evidence of mineralization. It can recognize connections between previously disparate deposit types. I'll show some examples of that. And it has the ability to predict the yet undiscovered expression of economic mineralization. So when you look at some of the examples of successful application of a mineral systems approach, even though they may have not have called it that at the time, I put 3 of them up there on the screen for you. For Yeelirrie, there you have geologists that look at unconformity, roll front uranium style of mineralization. They break it down to realizing that they need a uranium-rich source and they need some reductants in the sediment package that it's going through. And then they look at paleochannels in the Yilgarn, a totally different environment, and say, but the processes look like they still could be working here. And then you find the discovery of the first at the time, this is around 1970, this is the first paleochannel uranium deposit that was found. Olympic Dam, breaking down the sediment-hosted copper system to having to have oxidized basalts that were a source of your copper, having to have big structures that these fluids could move through, and looking for trapping sequences sitting within the sedimentary package. When they drill through them, they find nothing of the sort. They drill right through the sediments. They go into the basement, but they find Olympic Dam. Again, a totally different style of deposit. Nebo-Babel, the targeting for Nebo-Babel, and there's people in the room that can talk to it better than I. But with that, they were looking at whole lithosphere architecture, controlling the flux of ultramafic and mafic magmatism, and that was used to target the position of Nebo-Babel in the West Musgraves. And in all of these examples, the prior presence of mineralization was not a factor in the actual targeting. It didn't enter into the model. It wasn't part of the ranking. Right? So I want to talk a little bit about some fundamental constraints on mineral systems. And a lot of this comes down to the physics of the system, which is one part of the mineral system that we tend to be neglecting. There's a couple of fundamental constraints here. One is that mineral systems take elements at low concentration in large volumes of rock, and they eventually concentrate them at high concentration in small volumes of rock. And really the only plausible way to do that is by advective mass flux, which means you need a fluid to do it. Okay. And ore deposits are therefore seen as the foci of large mass and energy fluxes through the lithosphere. And there's a lot of examples of that. I've got a couple on the left-hand side. Olympic Dam, one of the world's great ore bodies, also one of the world's largest breccia complexes. Perseverance, large Komatiite-hosted nickel sulfide deposit, also the hottest lava channel recorded on Earth. Norilsk, not only the world's great nickel sulfide deposit, but it's also the largest continental flood basalt province. It's also coinciding with a major mass extinction event. So when we look at the fluids that are associated with these mineral systems, there's a few more constraints on that are important to keep in mind as well. Number one, the fluid has to be low viscosity to be able to move and advect a lot of mass. It has to be available in large quantities over very short time frames, and we'll come back to the time scales of mineral systems in a second. And the fluid flux has to be highly organized, and by that we mean it has to be highly focused in both space and time. And one of the key advances that has a big effect on understanding mineral systems is the physics of understanding complex systems. So everyone's aware of chaos, right? Where you have small variations in initial starting conditions can lead to big differences down the road. Like a butterfly flaps its wings in China, there's a hurricane in the US type of thing, right? Here we're talking about the opposite of that. We're saying that despite the large range of initial starting conditions, we see a lot of patterns in geology. So we see that the Earth system tends to order into specific patterns independent of tectonic environment. And these patterns have a few key attributes. Number one, they're fractal in nature, and they often show scale invariant power law relationships. I'll show examples of these. And they often show ordering around a critical point or phase transition. Now, when the physicists worked this out in the 1980s, one of their key examples was geological, and that was looking at earthquakes. Right? So in earthquakes, you have power law relationships. So on the right-hand side is showing the Richter scale. The M, the magnitude, is a power law relationship. So we know, for example, that there's 10 times as many magnitude 4 earthquakes as magnitude 5 earthquakes. And we see this relationship whether we're in extensional environments, compressional environments, independent of rock type. We also see that in terms of fault size population, and the examples show in seismic data sets versus wells, so a different scale, but the same power law relationship. We also see it in mineral deposits. So at the top is the distribution of gold deposits in the Superior Province. In the bottom, shown with a linear scale instead of a logarithmic scale, is the gold deposits in the Yilgarn Craton, again showing a power law relationship. So this tendency of complex systems to order around a critical point is called self-organized criticality. And the key drivers to get a self-organized critical system is that you have to have energy that is input into the system at a relatively constant rate, that you put a threshold barrier in place that prevents that energy from dissipating into the sink. And when that happens, the system then self-organizes and transiently breaches the threshold barrier and in what are termed avalanches. And so you get these massive energy releases very quickly with very, very short time scales compared to the energy input of the system. So as long as you keep those conditions in place, you keep the energy coming in, you keep the threshold barrier, you'll keep the self-organized critical system behavior. So in earthquakes, you have the brittle crust, that's your threshold barrier. The energy is the constant motion of the Earth's plates. The energy is built up, but it's not allowed to dissipate. It builds up and builds up and builds up in the brittle crust. And then when it goes bang. Earthquake, that's as what the physicists call the avalanche. Right? And as long as you keep that in place, you keep that behavior going. And the size of the avalanches, or the size frequency of the avalanches, is proportional to the energy gradient that it's trying to disperse. And that's why when you're in areas that are really under stress, you get bigger earthquakes, more earthquakes. Right? When you're areas that aren't under stress, you get smaller, less earthquakes. So mineralization shows a lot of these characteristics. We see that mineralization is transient in nature. We often see multiple repeated fracturing of the same rock mass. We see that the deposits have the scale invariant power law relationship, which I've just shown in a couple of graphs. And we know that they display fractal geometry. So these diagrams show that concept. So at your left is just the general concept of a self-organized system. Energy coming in, threshold barrier put in place that stops that energy from dissipating into the sink. It self-organizes, and you get transient energy releases in very short times called avalanches. And on the right-hand side, we've translated that concept through to a mineral system style of concept, where you've got fluid extracting metals from some volume of source rock at some scale, transmitting that through, trying to transmit that through the lithosphere, and at some point, and often at nested scales, you put these threshold barriers in place. When that happens, you cause the self-organized critical behavior, and you get the mineralization in the exit pathways. And John will talk more about that when he talks about the formation of ore chutes. So this brings us to the critical elements of the mineral system. Now, there's a lot in this, and so I'm just going to focus on a few things, and in particular on favorable whole lithosphere architecture and the favorable transient geodynamics, geodynamic triggers that trigger this self-organized critical behavior. The idea being that to get the largest deposits, what you really want to do is you want to generate the most extreme energy gradients possible. And those give you the biggest, highest quality mineral districts. So first of all, we'll look at whole lithosphere architecture. So in this, it's how does architecture help to focus all that mass and energy through the lithosphere. So that's the problem we'd looked at before with the Yilgarn and the clustering of deposits. And many of you have seen the maps on the left, a different way of looking at the Yilgarn Craton, where there's it's an isotopic map. The way to read the map, it's of the late granite bloom that stitches the Craton. The way to read the map is the hot colors have melted, are granites that have melted older crust. The hotter the color, the older the crust that's melted. The cool colors are granites that melted younger crust, just a few tens of millions of years older than the granites themselves. And the thing to pull your eye into is that gradient in the middle of the map. That's interpreted as a paleocraton margin at around 2.7 billion years ago, and it's where most of the tier 1 nickel deposits have focused, and also when that margin gets inverted, it's also where the big gold systems happen. Interestingly, at the if you look at the bottom left-hand one, the greenstone belts go north-northwest in that part of the world, yet the nickel deposits still mirror around that Craton margin. So again, showing how the magmas have been funneled around the lithospheric route. We can take this down to the deposit scale and work by the Goldfields group and St. Ives at St. Ives and John Miller and the PMDCRC, showing that this fundamental architecture goes right down to deposit scale. They've shown an architecture that controls komatiite distribution at 2,700 million years, gets reactivated several times, controlling intrusives and other sedimentary packages, and then 60 million years later is reactivated again to control the distribution of gold deposits. So this message of reactivation of fundamental flaws in the lithosphere through time is the rule rather than the exception. And we can, using these isotopic maps here, the colors have been reversed. We can use multiple isotopic systems and take time slices backwards as well. So the bottom left one is a map of epsilon hafnium, the lutetium hafnium isotopic system. And here the older cratonic nuclei are in cool colors, and the younger juvenile material is in warmer colors. And again, showing the focus of the ultramafic magmas and nickel deposits around the margins of these cratonic nuclei at 2.9 to 2.8 GA when the Forestania Lake Johnson nickel came in. The example I like to use to talk about whole lithosphere architecture is Antamina, because it distributes, it shows it quite well. Antamina is among the top 10 mines in the world in terms of rock volume moved. It ranks in the top 10, I'm not sure exactly where at the moment in terms of copper deposits. It's a polymetallic skarn around an intrusive stock in the Andes. And an interesting thing about Antamina is that it's formed around 9 million years. But at 9 million years, you can show that it's reusing an architecture that was set up in the Incaean orogeny during a thrusting event. And it's reactivated that architecture when the intrusive stock has come in, and that's what's shown in the top two diagrams. When you step out one scale, or an order of magnitude there, the bottom left diagram shows where Antamina is, and it also shows in dashed lines a couple of trans-origin structures. Now, when you go on the ground, you can't actually map these. You can only map them by standing back and seeing that you lose anticlines and synclines on either side of the fault, or that the fold axes warp around these things. And the reason is because these are fundamental features sitting in the basement that have yet to fully propagate up through the overlying sedimentary package that's been abducted over top of them. In the bottom right-hand diagram, we've stepped out another order of magnitude, And you can show that these faults actually control major differences in stratigraphic package, indicating that they were there when these rocks were deposited in a back arc basin off the coast of South America in the Jurassic. So you've got a deposit formed at 9 million years, using a structure at 42 million years, using a structure that was at 150 million years. And Wally Witt has done work east of this in the eastern Andes and shown that these east-northeast trans-origin features were there at least as early as 300 million years ago. Right? So these features, when you look at them at the surface of the Earth, this is looking a long strike of them from the mine across to the next range. You can see the bedding as ridges going across, so there's not a lot of offset on any of these things, but there are these vertical fractures, which you may or not be able to see on the screen there. But they look relatively unimpressive. They look just like joints, but it's just the brittle tearing above something that's quite fundamental at depth. But at the level of mineralization, they're often very cryptic, right? And that's an important message for targeting. So there's the concept of these vertically accretive structures. They're structures that are rooted deep in the crust, often down in the mantle lithosphere, and they're continually trying to propagate through time over rocks that are either deposited or abducted on top of them. And they often, at the level of mineralization, have a very cryptic expression. They're not the obvious faults on the map, and they're usually found by tectonostratigraphic reconstruction. So some common characteristics of these structures: they're strike extensive, they're depth extensive, often through the lithospheric mantle. They have relatively steep dips when we image them in deep probing geophysics. They commonly juxtapose different basement domains that you can tell by isotope chemistry isotope or magma chemistry of intrusives. They're multiply reactivated with a very long history. Vertically accretive, as we said, and they're not the obvious structures at or above the level of mineralization. Now, when we look along these styles of structures, not everywhere, not every structure is heavily mineralized, right? And so one of the things that we've come to realize is that mineralization forms in very brief episodes in much larger magmatic deformation, metamorphism, fluid flow events. Right? So there's something that is causing a fundamental trigger for mineralization and triggering this self-organized critical behavior of mineral systems. So this is what we call these favorable transient geodynamic triggers. So when we date mineralization, the more we can date it, the more we find that it's just within the error of the method, right? So we started by thinking of these things as, potentially millions of years. Then we thought of them as hundreds of thousands of years. Now we're realizing that some systems are forming, we're into the 10 to the 4th range. We're into the tens of thousands of years that giant mineral systems are forming in. So these are very quick events from a geological perspective. So the idea being that you've got multiple stages of fluid flow and metal movement through origins. So in the instance at the left, when you've got permeability allowing a lot of fluid flow through the crust, you're forming alteration, you're forming metal anomalism. You may even form low quality ore, but you're not forming a high quality mineral district. You need something that puts a threshold barrier in place, and while that threshold barrier is in place, you have a brief period of forming high quality ore, and as soon as that dynamic disappears, you're back to metal anomalism and no ore formation. So some examples. You've got Cripple Creek, alkaline epithermal. You've got Bingham Canyon, porphyry copper. You've got Carlin, a totally different style of mineral deposit model. Very different from an economic geology point of view. Same geodynamic trigger. Interestingly, this is also the same timing as porphyry mineralization in southwest China. So there's these periods in Earth's history of reorganization that are causing, when the plates reorganize, we're causing these triggers, these geodynamic triggers. Closer to home in Australia, you've got the gold in the Western Lachlan, you've got porphyry deposits, and all forming at the same time. And interestingly, you get this period of mineralization recorded in Kazakhstan as well. So we recognize at least 3 environments that can trigger high-quality ore formation. One is incipient extension, one is transient compression, and one is switches in far-field stresses, and I'll go through a couple of each of these. Now, the key thing is that during these events, vertical permeability is clamped, or active permeability creation ceases, so that you're not allowing the mass and energy to get to the sink, which is the surface of the Earth. Yet, at the same time, you're still putting the energy and the fluid into the system. And so what that does is it forms extreme energy and fluid pressure gradients, and the system self-organizes to form high-quality ore. It will continue to do so as long as you keep that barrier in place. So an example of incipient extension, the example of Lahir, alkaline epithermal, and Solwara, a very gold-rich VMS. Again, 2 systems that you would usually keep in totally separate bins from an economic geology point of view. Here, same geodynamic trigger, and probably, in fact, the same volume of enriched lithosphere that's part of their source, which we'll talk about in a sec. In porphyry copper districts in Chile, the 3 largest porphyry copper districts all form individually within a few million years, within tens of millions of years of this compressive environment. And during each of these are during compression. So the largest districts, the largest copper districts correlate with these periods of anomalous compression where you've clamped the system and caused the system to self-order. And the diagram on the left, top left, shows, is from Rosenbaum et al., and shows quite nicely as that Nazca Ridge sweeps under the edge of South America. Volcanism, which is as those asterisks, right, shuts off where you put this under anomalous compression. You've clamped the vertical permeability, and you form ore. And as soon as that ridge moves away, the volcanism comes back, and the ore formation stops. The other key way to cause self-organization is stress switches. So when in many situations, you'll go from one plate configuration to another plate configuration. You switch principal stresses, and when that happens, there's got to be a time when the rock doesn't know which way to deform. It's essentially in a neutral stress state. Yet at that time, so you're not actively creating permeability. Yet at that time, you're still putting the energy and the fluid into the system. Right? So the example here is the Juno Gold Belt. All of these deposits up and down this belt are dated within the resolution of a million years, at 55 million years, when the Kula plate went from orthogonal subduction to oblique subduction in the area, right at the stress switch, mineralization. After the stress switch, no high quality ore, right? Just at the stress switch. Okay, so just a few comments on fertility, and I'll just because despite having favorable lithospheric architecture, despite having favorable transient geodynamic triggers, not every volume of rock in those areas is well mineralized. You need another aspect, and that's fertility. So fertility is a geological region or time period that's systematically better endowed compared to otherwise equivalent geological environments. And there's 4 components to it. I'll only touch on a few of them. The punctuated evolution of the Earth's atmosphere, hydrosphere, biosphere, lithosphere. Pre-enrichment of the lithosphere in terms of fertility, an example there being gold. Geodynamic context, for example, magmatic hydrothermal copper, the work of Bob Laux, showing that the geodynamic trigger itself is also triggering the fertility. And in some systems, like sediment-hosted lead zinc, uranium, iron, and maybe some others, paleolatitude, particularly where you need ultra-high salinity or very high salinity brines. So I've got some examples there. Cooling of the Earth through time. The best example, of course, komatiite-hosted nickel sulfide deposits. You see them in the Archean, you see them a bit in the early Proterozoic, and then you don't see them after that. The evolution of the biosphere, atmosphere, hydrosphere, controlling the availability or mobility of metals. For example, you don't find unconformity uranium deposits before the Great Oxidation Event because you couldn't get uranium into a 6+ state and move it around. So what happens is when you form the first big intercontinental basins with a bunch of detritus that has never been stripped of its uranium after the formation of the supercontinent Nuna, the global oxidation event has happened, and now you put these oxidized fluids through and you just strip out truckloads of uranium and you deposit in unconformity uranium deposits. Sediment-hosted lead zinc, the same. Until you got a sulfate dominant ocean, you couldn't form the sediment-hosted lead zinc. But as soon as you did, you got a big swag of them. Just a comment on fertility and lithosphere enrichment. When you look at that slide, this is courtesy of Francois Robert from Barrick. Gold all over the place in the Andes. Yeah, favorable lithosphere architecture, everything, but the big deposits cluster, and that's what we're wanting to know is why. Now, empirically, we know that here they correlate with areas of flat subduction, and that's the areas shown by the black arrows. And Hronsky et al. Showed a model for how, when you get that situation, you can stall small volume partial melts in the mantle lithosphere that enriches the mantle lithosphere in gold, and then right after or at any time after that, you actually can have that gold transferred into the crust and form big systems. And this is probably the type of effect in the North China Craton. North China Craton has a big problem because the mineralization is in high-grade metamorphic rocks. The rocks are Archean, but the mineralization is Phanerozoic. So how do you do that, right? And the reason is because the gold's coming from below. And here you've actually had 3 subduction zones around that craton that's refertilized that mantle lithospheric root so that when it drops off and the thermal pulse comes in, you bring in the gold. So important implications of lithosphere enrichment is that we no longer can look and say this arc is fertile, or we have to think about it in terms of compartments along an origin. And those compartments are defined by trans-origin vertically accretive structures intersecting with origin parallel vertically accreted structures. And so the example on the screen there shows what would happen if you had part of that sitting under cover. You could be falsely led to think whether it was strongly or weakly mineralized under that cover. So, examples of nested scales, fertility in a geodynamic context. South America is a great example because South America, in the Cretaceous, started to move faster across the Pacific plate. And so it's now the area of the largest amount of flat subduction on Earth. It's an anomalously compressive margin. And then within that, we've got these transient, super anomalous bits of compression that have clamped the arc, ponded magmas at depth, allowed fluids to build up in these magmas, and the system self-orders, it forms high-quality ore, and then as soon as that goes away, it just forms metal anomalism again. Paleolatitude, the diagram on the bottom right shows that sediment-hosted lead zinc forming within 10 to 30 degrees of the equator in the hot zones. That's because it needs to be in the brine factories to get the saline fluids. And we find that with SEDEX, hypogene, BIF, uranium, probably all need these types of fluids. I'll just finish on the links that the mineral system allows between different deposit styles that have previously been thought of totally different deposit models. And I showed some examples already. A good one is the Alexander Triassic Metallogenic Belt in British Columbia, where you can look where you go from shallow on the shelf down in the southeast to deep basin in the northwest, and also you see different styles of mineralization along that rift that correspond with where you were in the rift sequence. So essentially, all of these, part of the same mineral system, just different expression at different place they were in the Paleo Rift. The challenge in mineral systems is keeping the scale of when you apply, is thinking of the scale of the process that you're worried at for the scale of the decision you're making. So for example, when I'm looking at large scale, I'm not even thinking of depositional sites. And it's actually not until, and I'll just go through this quickly, it's not until I get down to the deposit scale, right, when I'm actually targeting within a camp, now I'm worried about depositional sites. But if you look at the way that most of us do targeting, even on a regional scale, we've got trap sites or depositional sites or whatever we want to call it in our mineral system model, and that often weights really heavily because that's often where we have the most information. Right? Yet at the scale of regional targeting, it's actually not relevant. And so there's my last slide, which you've already seen. So the key thing we wanted you to take away, this new way of thinking of the mineral system in terms of fertility, whole lithosphere architecture, transient geodynamic triggers, and in particular, understanding this aspect of self-organizing critical behavior and how that changes how you look at the mineral system, and then how you take it and then you'd apply it in terms of looking for high-quality mineral districts.